Okay, I'm Roland Bechmann. I want to talk a little bit mainly about a project we are designing in Moscow. And I want to talk about how the design of this project relates to the sustainability certification and how this really helped us, this tool of the certification helped us to improve the design here under the special conditions in Russia. Just a few words about us, who we are. We are an international engineering office mainly. Our core disciplines are structural engineering and facade engineering. By the time we widened this a little bit and we're doing sustainability engineering and MEP engineering in some portions or in some areas of the world. We have our headquarters actually in Stuttgart, Germany, but we have offices all around the world, and one of the biggest offices besides Stuttgart is actually in Moscow at the moment. Just to see a couple of projects we've been working on and how much we appreciate really what the council is doing. So we worked on this KfW bank in Frankfurt, which was voted as the best tall building in 2011 worldwide by the council. The ADAC headquarters in Germany, which was a finalist for Europe last year in the voting. The Post Tower in Bonn, which just received the 10-year award, or other buildings all around the world. Sergio just made a very good presentation about one we were helping Jan here in Shanghai. But today I want to talk about this project. It's called Plot 15 in Moscow, Russia. And the building, or to start this way, what was special for us is really that we were involved in all design disciplines. This is because we have a very strong Russian office who is licensed for all disciplines, and we have a very good team there. Ivan Tomovic, who is running the office, is very well experienced in managing the design process. So there we started out with structural and facade engineering, but we also have the client who has his own architectural team with the construction documents and the architecture. And we did the MEP design and the energy simulation for this building. So it was a very interesting process in our office, since we were all kind of fighting for the same goals here. It's a commercial building, 283 meters high, if they don't change the height criteria in the other room at the moment. So we have these twin towers. They're interlinked and or connected by sky gardens. And we have a podium building at the base. Here you see a picture of the sky gardens. This, of course, helped a lot to improve the comfort in the building during the design phase. So all the high-rise buildings in Moscow City are here right in this area, which is west of the Red Square. So there's a new high-rise area in Moscow. Most of you will know it. If we see this, we are looking here. It's black and white, so some of you might not recognize the building. The building I will be talking about will be here. So this is a Federation Tower, which is already constructed. I think Matthias Lassen, the project manager for Chovan at that time, the architectural project manager, is here, so he could tell you about this building. And I think Joost, he will be talking about this building right after me. So it's actually very interesting that we have two projects in Russia here in this session. Okay, it's a commercial building, so the towers are filled with offices. It's altogether, we have 430,000 square meters. The podium building has a lot of parking, or it's mainly parking. Of course, we have a conference room in the podium building. We have shopping and retail at the base, of course, to attract people. But the use is really mainly office. This is the BIM model we were doing. So since we were working with all disciplines in our offices, BIM was, of course, a very good tool for the design optimization. Joost will focus more on stuff like this, I think, in his presentation. What was also special about the project is the foundation and how the podium linked into the foundation, because we had to face that this building, that there was already an erected and existing basement, since there was a previous design for the same plot and they have already built the basement. Then the financial crisis in 2009 came and the client had to downsize the building, so we were involved in this redesign, and actually we had to match the new design with the existing basement structure. Okay, just to give you some thoughts about the structure. I'm a structural engineer, so I will talk about all disciplines. However, this is the one where I was, of course, involved in most. So it's a mega frame structure. We have altogether four concrete cores, and the structural height for us engineers is 275 meters because there are some facade elements at the top, of course, but the real building height for the structural engineer is 275 meters. It's, the podium is 96 times 116 meters, and it's a concrete structure. The two towers are connected by these X-braces so that we create really a mega frame structure. Since we had to match with the existing column grid of the basement, our column design, it was actually hard enough to fit cores which were matching with the existing basement because of the foundation below these cores was already in place. But of course, we couldn't match the new columns to the old design. So we had to transfer the columns in the podium building, the column grid from the towers where the columns were, of course, adjacent to the facade. We had to transfer it to the column grid in the basement. We typically do this by using inclined columns instead of using a thick transformation slab. We like to use inclined columns because this simply saves material. And as a result, of course, you do get horizontal deviation forces because of these inclined force flow. You get these deviation forces which are horizontal and act on the core and on the slabs. And this was, of course, considered. So two of these slabs in the podium are really strengthened with embedded steel profiles to accept these loads. So there's a part of the structural model there. Okay, here you see the orientation of these forces. One other thing about the existing basement structure, when we went on the site, we found, of course, that they have done the last floors with quite a rush and a hurry, and in addition, the floor were unprotected for at least 2 years. So we were facing a lot of cracks in the existing basement. This we had to take care of this, of course, in our existing structural models. So they changed. We had to reduce the stiffness in these models to really account for these special conditions. And this is a column where we had to only strengthen a couple of columns since the load flow was a little bit different than in the old design. But in general, actually, the columns were able to accept also in the basement structure the load we are adding since the previous design was much bigger. Okay, let's now talk a little bit about the facade. When we design a facade like this, especially in Russia, we typically try to combine proven and solutions we've already tried in other buildings and maybe combine them in the best possible way to really optimize the energy and really provide good thermal insulation. So in Russia, we would typically not go to the very, very cutting edge of new technologies since it's really hard to get the stuff on the market there. So what we have these shadow boxes which are in front of the facade. In front of the slab, of course, they cover the slab. They provide additional thermal insulation. We have a very transparent facade here. About 60% of the building is transparent. And we have these vertical boxes, which also allow for natural ventilation. And this was, of course, done to improve the user comfort. Of course, we have sun shading and light control. So it's fairly, I would say, European standard, but combined in a very good way that actually fits to Russia. So to meet the sustainability goals, the client wanted to have a LEED Platinum building. We were using triple glass with slight sun protection coating, so a U value of 0.6. We have these motorized flaps here, so they allow for this natural ventilation, but just as a user comfort element. Okay, so of course the building is mechanically ventilated, but in addition to this, you can kind of overrun in your own room the mechanical ventilation to have a good user comfort. We have the shadow boxes in front of the slabs. We have about 60% transparent facade area. And as I said, it's a combination actually of well-known elements, but I think to a quality which you typically do not see, but hopefully we'll see more in the future in these buildings. The outside conditions in Moscow are, of course, very harsh. We have minus 30 degrees Celsius. So this had to be taken in account for in our design. And of course, when we design this, we always check whether all the elements will really go up into the building and if we can install all of them. But this is something which we typically do very early in the design process. Since the cores were quite big here, this was actually not a big issue. The entire facade was, of course, optimized according to the shading analysis. Actually, there is very little sunshine on the building because it's protected by all these other buildings or shaded by all these other buildings in the surrounding area. And about the energy consumption of the building, actually the energy provided to the building mainly came from the city grid, the city district heating system for once, and the city grid electricity. Largest demand were heating, domestic hot water, and lighting, of course. We had no cooling actually for the office spaces in Moscow. No cooling was necessary there. We needed some cooling for the podium, especially for the retail area, of course. So the total baseline building energy demand is 70,000 megawatt hours. And this is the diagram of the energy consumption. So really most of it is space heating, lighting, and service water heating. So to summarize again the energy efficient measures for the building, we have a high-performance building facade, building fabric as a passive measure. The next passive measure is good solar control of the facade. We have very good daylight penetration. As active measures, we have heat recovery, we have speed air handling systems, we have controlled lighting, heat rejection from the chillers, controlled ventilation for the parking areas, and of course, we also have free cooling when outdoor temperature is low for the podium building. What was a big discussion actually was the ventilation system was a long discussion, and of course also the water supply. And in all these discussions, actually the client's goal to achieve LEED Platinum was the only vehicle we could use to convince them of really advanced and design solutions. But in the end, this was a very good process so that we can deliver a very good building to the client. The energy efficiency was simulated according to ASHRAE. So from this baseline demand of 70,000 megawatt hours, we could reduce it down to 53 megawatt hours, which was actually a very, very good result for this location. And as I said, the real vehicle was always the LEED certification. We were talking a lot about the LEED certification with the client in this project, and his goal was platinum, so we had to collect at least 80 points there. And this is actually maybe interesting for you. Where could we collect all these points in Russia? What is really what was our approach there, and what can you actually really influence? So if you look at the categories, so this is from the LEED pre-certification. We have the platinum pre-certification now, so we collected 84 out of the 110 points. So where did we get them? For the first 26 points, we were actually very lucky because your influence as a designer is close to zero, because typically when you get into the game, the client has already picked the site, and this is a very dense area, very good transportation system there in Moscow, actually a very good city grid. So the client, I must say, collected 26 out of the 28 points just by choosing this location. We did a lot on the water efficiency. This is something you can do. I think we used really systems to save water. We used stormwater. We had green roofs. So this is something where you can really react as a designer or act as a designer, and where there was no real interference with maybe other than costs and convincing work to the client. But if you could show them that you would collect the LEED points, it was quite simple. But it's not really interfering with other design aspects. Of course, energy and indoor environment quality are always a little bit contradictory sometimes in some parts. So in our design process, there were, of course, hard discussions. The guys responsible for the indoor environment quality had long evenings with the guys from the energy and atmosphere design aspect, because sometimes if you add quality here, it's really worse for this condition. And me being a structural engineer, continuing with the good things, we collected, of course, the design points for innovation and design process, regional credits, because it's really, I guess, at the high level in the region there. However, me as a structural engineer, what's frustrating me a little bit is that we could only collect 3 out of the 13 points for the materials and resources. And this is not really because we were too lazy to optimize the building or so, but really this, as the system is set up right now, the LEED 2009 system, it's actually very difficult because these points you can only collect with using recycled materials, using green concrete, fly ashes, and of course something it's very easy to design, but when we talk to the clients, when we talk to the contractors, the supply chain for these materials in Russia is not there yet. So this is something where the process needs to improve, and of course we as designers, the first goal is always to have a design where the client can actually, where you deliver a design to the client he can build. So we didn't want to put too much pressure on this process in the client because most of this is really driven by industry practices. So we have this LEED Precertification Platinum now. And maybe what I want to add to the discussion, and maybe to the discussion we already talked about in other sessions. So when I'm thinking of the very first day when we talked about this life cycle assessment discussion, when we look at this, we, for example, often look also at the German rating system. Of course, all systems have advantages and disadvantages, but maybe just as an interesting point, there are some aspects in the German rating system, the so-called DGNB system, which would actually help us to improve, from our perspective, the design quality even more. So one thing, which is something the clients prefer a lot in Germany, that's why they're choosing this system, is the economic quality. So this is really equal to environmental quality in the German rating system and to social cultural quality. So there the client is really much in favor. But a big difference here from this category, environmental quality, which is of course a little bit similar, and I'm going back now to the energy and atmosphere and water efficiency quality. But the big difference is you're not looking for individual measures, but this really addresses the overall energy demand of the building over the life cycle. Okay, so it's not that you look at individual measures, but you do perform a life cycle analysis according to European standards, and it doesn't matter where you reduce the energy. Okay, so if we have this in our design work, for example, reducing materials and reducing the structural weight of a building would actually be a part of the holistic approach, and what you could actually even, for example, with insulation materials, there's a big discussion. How much insulation do you add? Because at some point of time, the additional insulation you add is actually negative for the entire energy calculation, for the life cycle analysis. So this is something where we, from our perspective, coming from maybe sometimes German design thinking, we think this is also something where LEED has improved, but actually I think the next step is that there's one big energy count for the full building. This is now going back to structure. We have special tools, of course, how to optimize the materials. Typically, we have a tool now where which not automatically optimizes for stresses, but also for deflections. So it's not that you have the individual engineer anymore sitting there and optimizing day for day. You simply set the goals for deflections, press a button, and the system is running overnight to really optimize the structure for all the deflection criteria which have been set before. And once you really have we all know as structural engineers now, going back to this, we all make these comparisons of slab systems. We make tables with the cost, with the embedded carbon. Everybody knows that. And I don't know what your experience is, but most of the time, you pick what is typically what the industry practice is there. Okay, most of the time you have all these numbers and figures, but the client will say, or the companies will say, hey, we are in Russia, we are making a concrete slab, and that's how it was, of course, in our building, and we're making a flat concrete slab. That's the same how it would be in Germany. Maybe in the US you would make a post-tension slab. But as long as it's really not the optimization of the material is not an inherent part of the rating systems, at least. And I think Ron Clemenchit was even talking that there's a carbon, politicians in California talking about a carbon tax. I mean, that's maybe a step ahead, but I think that we really need something in our systems that the material reduction pays back. Okay, and the German system is one example, but of course I think this is something where we, from our perspective, have to change industry standards, because there's so much, and there were other slides. I will not show them. We had many here in this conference where you could see how strong the impact of the materials and the resources in the overall life cycle assessment are. Okay, because here in this building, of course, we did this calculation. What happens if we bring it down, if we further optimize it, if we were fully free in the choose of the system, which we were not, okay, because we are always linking to the industry standards. And since here we couldn't collect additional points by, for example, changing the floor system, there was really no need for the client to go for this option. And it's actually not the way, as it's often argued, that simply because you reduce the materials, you reduce the price, and that's the argument for the client. Often it's really that the cheapest solution is a common industry practice wherever you are building. But of course, by reducing the material, you can have actually, and this is calculated according to this DGNB standard for the life cycle analysis, you can save up to 18% in all the relevant categories for primary energy, global warming potential, and yeah. Okay, just a teaser. Maybe what are we also doing? What is really the next step? We have to change the materials. Maybe we have to change the way we are building. We in Stuttgart have a very close cooperation with the University of Stuttgart, where we are researching on new materials, where we are researching the way we will build in the future. And one aspect is, of course, that we have to come down with the resources. So are we looking how, for example, how can we do that? How can we further reduce the energy? And one method is really that we're looking for new concrete. So we have a gradient concrete, which is actually a little bit derived, or a little bit came from studies which we did with bones. So of course, the stress, if you put a stress diagram on a bone, you will see that the bone has the most material where the stresses are the highest, and that it's porous at the inside. And this is actually how we see the concrete structure in the future as well. So we are looking for concrete with porosity, with air maybe in the middle of the slab, for example, to reduce the weight, even if we have a general flat slab, and even if we want the thermal mass at the outside of the slab. So these are kind of new materials or changed materials we are looking in for the future, and we have the first prototypes, for example, for a slab where you actually have the full material at the outside and the high porosity and the form at the inside of the slab. So this really brings down the overall mass and reduces the mass of your building. In general, there's a lot of discussion about whether to use steel, whether to use concrete, and of course, you do see all of this in the life cycle assessment. I guess concrete is in general a material, if you look at embodied energy versus strength, which we as structural engineers do. How much embodied energy do I have? What structural strength do I gain from this? Concrete is actually a very good material. In this category, it's better than metals or steel. Okay. Of course, the recyclability of the steel is better and adds you or gives you additional points in the life cycle assessment. So this is also the next step where we have to go. But maybe coming back to a quote Anthony made earlier in this conference, all these life cycle assessments are, of course, based on a building period, which is, for example, in the European codes 50 years, it can be 60 years. But in general, we should all design the buildings in a way that we can demolish them. And I think there were good presentations here in the conference how we can do that. However, on the other hand, for the high-rise, super high-rise buildings, 250 meters, 400 meters, 600 meters, actually I agree with what Anthony stated earlier, that we should really design them forever. okay, because it will be so difficult to take them down. There the approach should be different. And then the recyclability of these materials is, of course, actually less relevant than the overall embodied energy we have from the beginning.